Hello, these are videos for a revamped Class 17 handout. There are two reasons why I remade the handout and I'm posting these videos. The first reason is I wanted to simplify allylic halogenation, the one with either BR2 and NBS. I am going to stick with just NBS, and that way it's not confusing when I have BR2. BR2 for us in this module will be radical halogenation of an alkane, whereas NBS will be the allylic halogenation of an alkene. I know those words are a little bit jumbled in your head. It will become very clear as you work through this handout and these videos. I just want to assure you that the changes that I made to the handout simplify what you need to know. It was too complicated what I was doing on Friday. The second reason is the information that I gave each class is inconsistent. There were some things I remembered to tell the 1030 class that I forgot for the 1145 class, and vice versa. So both classes got good information, it was just incomplete. And because this is the first module after your second exam, I do want everyone to be on the same footing and get off to a good start. And we're going to have all of the Class 17 handout on videos. That way, again, you know exactly where to start studying and what to start studying when you review for your exam number 3. With that being said, let me get through at least page 1 for this video. A lot of the information that I gave you on Friday is, well, all of it's accurate, and some of the stuff here is going to seem very familiar. I just want us to start cleanly with a new handout, and I have some new figures also that will clarify a couple of orbital concepts. Okay. Haloalkanes can also be called alkyl halides, and an example of an alkyl halide looks like this. And the name of this is 2-bromobutane, and it follows the convention of the halo followed by the alkane, the halogen followed by the alkane. But either term is fine to use. In this module where we are looking at radicals, those are molecules that have unpaired electrons, and one example of that is shown to the right over here. Well, it's a generic example, and to show the movement of single electrons, we're going to use fish hooks. If you look very carefully at my fish hook, it has one barb versus the 2 barbed arrows that you've been using all along when you were drawing mechanisms. Let me show you this in action. For hydrogen peroxide, we're going to do what's called a homolytic cleavage, where each atom of a single bond gets one electron, gets an extra electron. I'm not going to use an equilibrium arrow in this case. I actually don't use it a lot for radical mechanisms. But we have HO radical. You could put the lone pairs if you want. Right? There were 2 lone pairs to begin with, and we obtained a single electron. Or you don't have to. If it's a radical, you could just draw the one unpaired electron. Now, with radicals, the stability of radicals follows the trends that we saw with carbocations. So tertiary is more stable than secondary and more stable than primary. Before we look at the stability trend that I have written down here, why don't I show you how to draw resonance, mechanism arrows for resonance for radicals. Just like we had carbocations that could undergo resonance, we have the same thing for radicals. Now, in this case that I have drawn here, I am going to move the single electron to the bond next door, and I'm going to complete the pi bond by moving one of these electrons of the pi bond shifting to the left. That pi bond that I just used has another electron, right? It has 2 electrons. We're going to shift that last or the second electron to the right to that carbon. Now, why would I do this? Look at the result. Just like carbocation resonance, you typically shift a pi bond to get a new carbon that's naked. And that carbon that's naked, in this case, it's a radical. But you've seen this with carbocations as well. The type of radicals is the same nomenclature as we had with carbocations, primary, secondary, and tertiary. And we have this. With enough practice, you should be able to draw the resonance structure without having to draw the arrows, but you still need to know how to draw the mechanism arrows in case I ask you to do that. Now, I mentioned here that I don't think I said this in class for either section. You know, carbocations are stabilized by hyperconjugation, right? When you have the more alkyl groups, you have more hyperconjugation, meaning that I'm not going to get into it too deeply, but the sigma bond next door donates electron density. What arrow do I want to use? Donates electron density into the carbon next door, in this case an empty p orbital. And we see the same things here with the radicals, because radicals are also sp2 hybridized with a p orbital. I'll get to show you that at the very bottom. But before we do that, let's do the stability trends, or look at the stability trends. This is a methyl radical. Okay, next we have a primary, secondary, tertiary with resonance, and another tertiary with resonance. Now the thing with this is that, how do I differentiate between these two? They're both tertiary with resonance. You have to analyze the resonance structures and average the stability or the substitution of the two parents, the mom and the dad. Let me show you what I mean. I'm not going to draw the mechanism arrows. We saw that already up here. But it's the 3 mechanism arrows to get from one radical to the next. This one over here, I have this new resonance radical. What I noticed for the one on the left, this is secondary, and this is, again, tertiary. When deciding who is more stable, this or this, you need to look at the whole radical, meaning you need to look at the hybrid or visualize the hybrid of all the parents or all the contributors together. Same thing here. And so to determine who is more stable, I am going to average the resonance contributors. So tertiary and secondary, halfway is like 2.5. Okay. I'm not going to write that down. Just think of it as halfway in between a tertiary and secondary. That is the substitution of the, we call it the kid, the offspring of the mom and the dad. But here we have tertiary. So the kid, the hybrid, is, I would consider it tertiary as well, meaning that this is more stable, okay, because literally the radical is more stable than this radical, okay? Now, what could be super tricky is if I drew these two on an exam, these two, you may automatically think that this is the more stable, but you have to still do the combination of all the contributors together. That wasn't the best example, but just because this is tertiary and this is secondary doesn't automatically mean that this is the major or this is the more stable radical, because you have resonance. what if this resonance was primary? Okay, if it was primary, then this would be the more stable radical. Okay, or you could circle these two would be the more stable radical. Tricky concept. If you need more explanation, come see me and drop in hours. But again, you're looking at the hybrid, literally visualizing the hybrid. Okay, last thing on this page is the orbital diagram. And this carbon right here, let's take a look at this one right here. You see that? That carbon is sp2 hybridized. So an sp2 hybridized carbon, let's take a look at this one at the bottom on the left. You know, this one is sp2. This one's sp2 as well. This one's sp2 in terms of the orbitals. But we know we have a p, and it includes both lobes. That's an sp2 carbon. In big black dots, here are my 4 valence electrons. So yes, I like to think of this unpaired electron right here. That electron is contained in the p orbital right here, which is very interesting. What am I drawing here? I'm drawing literally this one here, I think. Okay, with the radical here being this one. Yes, and these 2 sigma bonds here and here. Now we have a 3rd sigma bond going to this carbon. What you notice in the line structure is that this carbon, and this carbon, they're all sp2. And that's why I have 3 carbons in a row that have p orbitals. P and P. And look at this here. That's a pi bond. So if I'm drawing the orbital cartoon, there's your pi bond, right? One there and one there. When you look at, this drawing, where we have 3 carbons in a row and they're all sp2 hybridized, take a look at this. PPP. Okay. Did I do this correctly? Let me make this the same color. I'm just a little particular about that. All right. PPP. PPP. Well, how do I know which 2 P's are making the double bond? You don't. See, the kid is a combination of these 2, and no pair of carbons has a full double bond. It's 1.5, 1.5, 1.5, 1.5. That's what we have here. Now, I think that it's if you have models, or just take a look at my models, literally, I think people are still forgetting that this is flat, trigonoplanar. So this is also a good model to show flatness. What do I mean by flatness? Look at this sp2 carbon here. See how we have a p orbital here? But look what's flat. That bond, and this bond. And so if your radical is here, it could equally be in this lobe. So it doesn't matter which lobe. And when we get into reactions, when we add something to this carbon, it could come from the top or the bottom. If this was sideways, it could come from the wedge or the dash. That's what I mean by flat, that there's a 50-50 chance to attack from either side. So the flatness is, I don't know if you can see this, is that. And we could have addition to either lobe of the p orbital. 50-50. 50%, 50%. Okay, so the drawing does 2 things. It shows us how we could get racemic mixtures, because the atoms around a radical carbon are trigonoplanar. And it shows us that because the p orbitals are aligned, we actually don't have like a true double bond or a true radical. It's shared. These 3 carbons share these 3 electrons. Okay, and Either drawing, either this one on the left or this one on the right, are acceptable, but they're not the true picture. That is page 1. I think I'm going to stop there. The next video, I'm going to try to put page 2 and 3 together, but this is good. I got to, this is new, this photograph here. So both classes now have it, and I think this is a better way, or I think people can see it a little bit easier when you see my model and the drawing of the orbital cartoon, and you're not, scrambling to copy what I draw on the board. It's the template is right here. Okay. Before I leave, let me put in the other valence electrons, right? Okay. And you know that picture represents this molecule here.